Hi everyone. Today we're going to be discussing Unit 4, Target 2, which is find the force from a spring and the energy stored in the spring when it's stretched. So, this is kind of your typical graph of a Hookean or linear spring. And what's unique about a spring as compared to other forces that we've studied is that the force of a spring increases the more that we stretch that spring. And that's something that's pretty intuitive to us. We know that the more we stretch a spring, the harder we have to pull it. And that's different from kind of normal forces. Typically, the forces that we've studied up until this point are constant, regardless of the position that we're applying that force. I've kind of written that out here, what I just said, just the idea that what makes a spring unique is that the force applied is not constant. The force of the spring increases the further that we stretch it from its natural length. Okay? So, let's try and visualize that a little bit. When a spring is at its natural length, we don't have to apply any force to stretch it or have it at that point. But let's say, in this case, we stretch it to 0.2 meters. To stretch it to 0.2 meters, we would have to apply a force of 20 newtons. On the other hand, if we want to stretch it 0.4 meters beyond its natural length, we're going to have to apply a force of 40 newtons. And so, yeah, just like I said, the more we stretch a spring, the more force we have to apply. Let's contrast this with, like, say, force of gravity. Let's say we've got this 10 kilogram box at these three positions, these three heights, right? And let's say that we wanted to compare the force of gravity at those three heights. Well, we know that in order to do that, we do mass times the gravitational field strength, and so the force of gravity here is 98 newtons. Well, the force of gravity at this height, the next height, is also 98 newtons, and the force of gravity at the next height is also 98 newtons. So you see, it doesn't matter what height or position this box is at, the force of gravity is going to be 98 newtons, so long as we're close to the surface of the Earth. Similarly, we've studied friction, and let's say that same box is sliding across the ground to the right. If that's the case, it's going to feel friction on it opposing its motion to the left. Well, let's say hypothetically that force of friction is 6 newtons at this point while it's sliding. Assuming that the box's mass is constant, that the ground stays level, that the two surfaces, the bottom of the box and the ground, stay the same, that force of friction is still going to be 6 newtons at the next moment in time. And yet again, at the next moment in time, the force of friction is going to still be 6 newtons. So we see this is what makes a spring so unique. That force changes as we stretch the spring. Whereas, like, say, the force of gravity or the force of friction, those forces, similar to the other forces we've studied up until this point, those stay constant regardless of the position that the object is at. Okay, so let's take a look at this in the context of, like, say, a problem. Let's say that we want to find, for starters, the spring constant K for this spring. Well, we know that our mathematical model, or the equation that for force of a spring, is kx, spring constant, times x, the distance that is stretched beyond the natural length. If we rearrange that to solve for k, we see that we get force spring over x. And that is going to be the slope of this graph, because force springs on our y-axis, and x, the amount that it's stretched from its natural length, is on our x-axis. And if we do y-axis over x-axis, we get our k value. So let's go ahead and pick some points, or actually find the rise over the run. Let's say that we want to go from here to here, and here to here. We can say that this graph rose positive 60 newtons, and it ran positive 0.6 meters. So when we stretched it 60 newtons, when we applied 60 newtons of force, it stretched 0.6 meters. So we can plug those values in and find our K value, the spring constant, and for this spring, the constant is 100 newtons per a meter. Cool. Next, let's find the energy stored in this spring when we stretch it 0.4 meters from its natural length. So there's, so to visualize this, there's the natural length of the spring, and then here is a visual of us stretching at 0.4 meters beyond its natural length. There's two ways we can solve this problem. The first way is using the mathematical model. And we know that our mathematical model for energy stored in a spring is 1/2 kx squared. So k is our spring constant, x is how far it's stretched beyond the natural length, and therefore 8 joules of energy is stored when we stretch our spring 0.4 meters beyond its natural length. Okay, but there's another way that we can solve for the energy stored in the spring when it's stretched 0.4 meters from its natural length, and that is by applying our graphical model. And the area under the graph from 0 to 0.4 meters is going to be the energy stored in the spring. Let's remind ourselves of why that makes sense, and it basically boils down to unit analysis. When we find the area of a graph, we're really multiplying what's on the y-axis by what's on the x-axis. And when we look at that in this case, we see that we're multiplying force by stretch. And so the units of force are newtons and the units of stretch are meters. So we've got newtons times meters, which we know are joules. So the area of this graph is going to be joules. So if we find the area under the graph from 0 to 0.4 meters, it's a triangle, so we do 1/2 base times height. In this case, our base is 0.4 meters and our height is 40 newtons. And we find that it comes out to be 8 joules. And you know that you're applying your models right when you can apply two separate models, like mathematical and graphical model, and they come out to give you the same answer. That's a strong indicator that you're applying your models correctly. Now, a good follow-up question is to think about how much more energy is stored in the spring when it's stretched an additional 0.4 meters. So what does that look like? Well, that looks like this. It's already stretched this much, but if we stretch it 0.4 meters more, in other words, a total of 0.8 meters, then how much more energy was stored in it while we stretched it that additional 0.4 meters. Let's take a look at that. Well, we'll start with our mathematical model. And we can start by doing 1/2 kx squared, where we plug in 0.8 for that x. This is going to tell us the energy. X, however, is always the change in position from the natural length. So this tells us how much energy is stored in the spring when it's stretched a total of 0.8 meters from its natural length. The question, however, is asking how much additional energy was stored when we stretch it the additional 0.4 meters. So in order to find that, what we need to do is we need to take the difference of our two energies stored. In other words, we know that there was 0.8 joules stored when it was stretched 0.4 meters, and there's 32 joules stored when it was stretched 0.8 meters. And so if we take the difference between these two things, we find that the extra energy stored in the spring was 24 joules. Well, let's see how this plays out using our graphical model. Again, we just need to find the area from 0.4 to 0.8 meters. So if we find this area, then we'll find the additional energy stored in the spring. See, this green area was the energy stored for the first 0.4 meters, and this orange area is going to be the energy stored for the next 0.4 meters. Well, we see this as a trapezoid, and so we can apply our equation for a trapezoid, which is 1/2 base 1, and so base 1 is going to be 40 newtons, plus base 2, which is 80 newtons, times the height, and the height is 0.4 meters. So when we multiply all that together, we find, sure enough, 24 joules of energy was stored. So an additional 24 joules of energy was stored in stretching the spring 0.4 meters beyond the original 0.4 meters it was stretched. There you go. That is Unit 4, Target 2. I hope that was helpful. See you later.